Zhang from Xi'an Jiaotong University. The title of the talk is Multi-Scale Origin of the Electromechanical Responses in PZT.
Good afternoon. Thank you for inviting me to this conference, and I'd especially like to thank Journal of Advanced Dielectrics for supporting the trip. To supporting the trip for me to attend this conference. My talk is, well, this session is called New Materials and Solid Solutions. Well, obviously my material is very old. It's not a really new material, but we're trying to find some new technique to analyze the electromechanical response in this very classical material. Our work is mostly done in ESIF, the Swiss Norwegian beamline at ESIF, and we use PZT single crystal. So it was originally done when I was a postdoc with Professor Ye in Simon Fraser University. So our beautiful PZT single crystal is from Simon Fraser University. We've a bunch of us young people participated in the experiment in ESIF, especially Dr. Smyon Goffman and his then PhD student Hao Ming Chui brought the very important microcontroller to this experiment, and they also participated a lot in the data analysis and the development of the technique. So I'd like to start from the classical theory about the contributions for electromechanical response in ferroelectric or piezoelectric materials. So, of course, one is the intrinsic contribution. We can have a deformation of the unit cell by under the application of electric field. And of course, we have the very classical model of polarization rotation, which also causes deformation of the unit cell. All these can be analyzed by X-ray diffraction, also called diffraction method, because when we have a deformation in the unit cell, we have a shift of the position of the diffraction peak. So we can calculate the center of mass of the entire diffraction reflection, for example, and then we can have a general idea of how much the deformation it can be. Of course, we have extrinsic contributions in a multi-domain single crystal. So this, if we want to also use the diffraction method to analyze it, we observe exchange of the volume or the intensity of several different diffraction peaks. So, for example, like here, it's basically a reflection of the change of the volume of different domains. But if we take the whole thing, so this can be a group of a same family of reflections, and then we take them all into account, we can also calculate a center of mass. Basically, if this peak is higher, this peak is lower, then we have a center of mass closer to the large peak. And when we apply the electric field or switch the electric field, we have an exchange of the intensity. And then we have, it's very easy to imagine that we have a center of mass shift to this peak at lower 2 theta value. So by that, we're trying to use a very similar method for two kind of mechanisms. And by this, hopefully we can analyze the effect quantitatively. My title is about multi-scale. So really, when we talk about intrinsic effect and extrinsic effect, they are from different scales. So for example, we have mesoscopic domain one motion, and the intrinsic effect is from the unit cell level. So from the real space, they are actually at a different scale. But in the case of reciprocal space, when we try to analyze them from the diffraction data, most of the time they are messed up together. So for example, if we have this diffraction, one of the reflection, and it's sort of shifting or changing on the electric field, it's very easy that we interpret it as an intrinsic effect, because here we see one peak, and this peak is shifting. So it looks very similar, very look like an intrinsic effect. But if we have, for example, high resolution detector to fully look into the detail of this peak, we can see it has multiple components in one reflection. And of course, each component is shifting, but there is also exchange or change of the intensities, which is an indication of extrinsic effect. So we're trying to sort of separate these effects, including the intrinsic and extrinsic effect. And also, when we talk about domains have different sizes or different scales. So they are all mixing up now in the raw data, and we're trying to separate them. So our approach is to take multi-domain single crystal to synchrotron with a very high-speed, high-resolution detector, and we can apply alternative electric field, and the data are synchronized with the field, so we can separate the signals from different field states. So this is an experimental setting. So what I like to mention is we have a crystal here, and we polish them into the needle shape. We apply the electric field along the edge of the needle. And when we carry out the experiment, we can rotate this crystal at the phi. So by that, we can have a three-dimensional reciprocal reconstruction of the diffraction intensities. So this is the schematic of what's going on with the experiment. So this is the crystal. And we have a microcontroller here that was originally built in the University of Siegen in Germany. So actually, from this microcontroller, we can trigger the electric field from the Pilatus signal. So by that, we can actually realize the synchronization of the electric field and the detector, the process of data acquisition. And also, because in the beamline, the position of the detector can be moved in this direction. So now it is a setting for low resolution reflection experiment. But if we move the detector further away, and it is possible for us to focus on only one of the reflections, so we can get high resolution images. Before we look at the real data, there's one thing we need to define, which is a coordinate system, because this is easier for us to really analyze different d-spacing and the same d-spacing intensities. So for example, we have a high-resolution reflection. We can already see that inside we have several components of this reflection. And it is, for example, if it's 0 to 0, and then we define the x-axis always perpendicular to the reciprocal lattice vector. So if the reflection is 0 to 0, then x is perpendicular to 0 to 0. And then we define y and z to make sure that the yz plane is perpendicular to x. So if we move on to the next reflection, for example, 110, now the x is perpendicular to a 110 direction. And we also change the yz direction also to follow the rule that yz has to be perpendicular to x. The good thing about this definition is that every time we plot a 2D map with xy or xz, we immediately tell if there is a separation of different intensities along x. So for example, here we see obviously two intensities along x-axis. So we know they are basically occupying two d-spacings, two different d-spacings. So we see two domains with different d-spacing. But if we plot a two-dimensional map with the same x value. So we can basically cut a slice perpendicular to x. Then we have different components with the same x value. Then they have the same d spacing. And by that, they have they are an indication of also different domains, but these domains are the components with the same d spacing. So that is the intention of us to redefine the coordinate system every time. Okay, from that, then we can have some direct observation. We have a reconstruction of three-dimensional data of the reciprocal intensity. And we also have like each of them on each state of the field. So we can see the change of the high-resolution reflections on the different electric field states. What we care most is still how the center of mass of each reflection is moved or shifted, and if there is any intensity exchange happening when we change the electric field. Before that, let's mention a little bit about the crystal itself, because it's very important that we know the exact composition and the symmetry of this crystal. So we also measured a few high-resolution reflections under the different temperature, because in the case of a single crystal, sometimes it's not so easy to directly measure the ratio of different elements inside this crystal. So one way is to measure the phase transition process and to have a guess of exactly which composition it is. So this is a slice of the 220 reflection. And this is an example that we have x-axis here. So x is an indication of the d spacing. We can see from the room, at the room temperature, there are basically two major peaks and a small tail here. And we also can heat it up and see how these reflections change. And this is sort of a metastable state, and it forms a new phase with two small tails here. With more heating, hopefully the crystal enters into the cubic phase. So, and by cooling the sample down, it's basically repeat the same phase transition process. So from that, we can see there is a phase transition process from, we call it phase one. By one reflection, we can't really see what symmetry it is. And phase two, and finally it enters into the cubic phase. The phase transition temperatures are here. So we can see a very clear thermal hysteresis here. So from this phase transition change process, we have a guess that the composition of this material is 55% zirconium, which is on the left side of the MPB. The coercive field is around 10 kV per centimeter. So the field we apply is 14 kV per centimeter. Is comparable to this coercive field, which means during the process we are supposed to see some intrinsic effect and some extrinsic effect. But because this field is not much higher, it's not so much higher than the coercive field, so actually we didn't observe a complete switch of the domains. To have a full symmetry analysis, we did this HKL lattice parameter indexing with several high-resolution data. And the result is actually the monoclinic structure can fit the data reasonably well. For some of the reflections, a mixture of rhombohedral and monoclinic is slightly better, but at this stage we are accepting that it's mostly monoclinic. And this monoclinic is CM, so the monoclinic mirror plane is the 110 mirror plane. Okay, so to really analyze the response on the different electric field, we choose a few high-resolution reflections. So one is 002. So we have a 3D mapping of the reciprocal intensity here, and we can see there are several components inside, and they are probably in a similar d-spacing value. By having a three-dimensional intensity, the way to analyze it is always cut a slice and we integrate this slice, so we have a two-dimensional mapping. So there are several possible ways to cut it. For example, we can cut perpendicular to x or along x, so we can have different response. So our method here is to, so first of all, to cut the slice perpendicular to the reciprocal lattice vector. And by cutting it here and integrate intensity from a thin layer, we have a mapping, two-dimensional mapping like that. So we have this direction is x, and we have y and z like that. So this intensity, we can see there are several local maximum intensities here. So we labeled them as three different boxes. So these three boxes potentially means there are three different domains that can be seen from this reflection. They are at very similar d-spacing value, so they are basically, it's quite possible that they are only with very slight variation of the polarization direction. So by labeling this different component of the reflection, what we can do is to integrate the intensity within each box, like this very small box, because one box is standing for one domain. So when we integrate the overall intensity within one box, and then we can plot basically the integrated intensities within this box as a function of x. So now we are giving another one-dimensional plotting of how this, how the diffraction intensity change, just reflecting this one domain with the d-spacing value. So by having this kind of Bragg reflection, basically Bragg reflection, we are showing the Bragg reflection of only one domain, so one component of this reflection. The whole thing containing every domain that's shown in this reflection, and if we plot it against x, it will look like this. So they look quite different, and especially their response on the electric field are also different. So we can trace all these three boxes and their change on the different field states. So this is a more quantitative sum up. So first of all, we choose one state, and we put each Bragg reflection standing for one domain together here. So first of all, we can notice that they are actually at different d-spacing. So it is a gesture saying that they are different domains with polarization lying on different monoclinic mirror planes. So they are basically showing different orientations. And we can also plot their response on the different electric field. This is, I'm only showing the plus and the minus field, which is the switching. They show actually quite different response. For example, box 2 and box 3, they are changed, especially the center of mass shift is not so much. But the first one, we can see, first of all, the center of mass is shifted quite a lot. And also it's got a new peak, a tiny new peak emerging. So why is it? Considering its monoclinic CM phase, the monoclinic mirror plane is 110 plane. And the field is along 001. So in principle, all the polarizations on all the possible domains should be able to rotate under the effect of the field. But we see different response. So it is possible that the reason for that is the relative position of the scattering vector and the rotating plane. So for example, if the scattering vector is not in the in-plane with the rotation plane, then we probably won't see much. We can see, well, the effect is still there, but it can't be really reflected on our experimental result. But if the scattering vector is in plane with the rotation plane, then this effect will be massive, and we can see this effect very clearly. And also, by having a small shoulder appearing, by switching the field, we are actually seeing the polarization rotation effect from this monoclinic mirror plane. Okay, so now we're sort of really assigning different components to different domains. And now we have this smallest box having the signal from one individual domain. And we can also increase the size of the box. And here is a plot of the Bragg reflection of the whole area inside this box and their response on the different electric field. And we can see that it's actually changing by increasing the size of the box. And finally, it will be not changing anymore when all the domains are included inside our box. Okay. So just to make that video more easier to see, so I'm picking up 3 boxes with 3 sizes. So we still have this center one, the smallest box, and you've seen already that this is the response under the field. And we have an intermediate box, so the response looking like that. And of course, we have the largest box looking exactly the same as the overall X scan. So, and we have a lot of different plottings with the intermediate sizes. And from each of this plot, we can calculate, for example, the center of mass on the plus field and the center of mass on the zero field. And we can calculate, by changing the field state, how much of the center of mass is changed. So this is 1 point. Like each 1 point here is standing for, at this special box size, how much is the d-spacing change between plus field and zero field. So it's looking like that. And by having the box size increasing, we can see a smooth change of the d-spacing shift. So at this very small box size, we can see that some of the response are quite strong, like that. And by increasing the box size, we are basically including a lot of different domains inside the calculation, and their response are decreasing, which is understandable because different domains, they have different signs, plus minus signs. So they are having some canceling effect. We call it canceling effect. And finally, at about this scale, so we call it a characteristic scale, about 40 times 10⁻⁶ here. So they are basically not changing anymore. So at this scale, we are, in principle, we are including all the domains that cannot be separated from each other. There is another more important scale that we want to talk about is by having this kind of plotting, we have an estimation of the Bragg peak in the reciprocal space, and they are an indication of the domain size in the real space. So by having this simple calculation, we estimate that the domains that we are showing from different boxes having a scale of hundreds of nanometers. So exactly what this domain is, so we're trying to really relate it to the real space. And so here is a visualization of the three-dimensional reciprocal space. And before we had only one peak component, but now we have 2. So if we have 2, that means these 2 peaks, they have significantly different d-spacing values. at this one direction. So they form something like classical ferroelastic domains. For example, like in a tetragonal phase, the A domain and C domain, in a certain direction, they have different d spacings, which is very easy to understand. And these kind of ferroelastic domains can exist in all kinds of symmetries, and they are usually separated by a straight line of domain walls. And by slicing into one of the peak and having a plot of that, we selected different boxes, which is the analysis we just did. They have the same d spacing, basically the same d spacing. So imagine if we have a high symmetry crystal, for example, tetragonal rhombohedral, they should be forming the classical ferroelectric domain with different sign, plus, minus, but they are sort of 180-degree domains, looking like that. And they sometimes observed by PFM, and combining the PFM with the optical microscope, they are usually found embedded inside, for example, like this, inside one of the ferroelastic domains. And it's actually consistent with our estimation that these small domains are the nanometer size or nano size. The only difference is that in our case, we observe these domains, they have slightly different d spacing. And the reason is we have a monoclinic single crystal. So this crystal, we still can have plus and minus signs of domains, but they don't have to be exactly 180 degrees with each other. So because of the polarization are slightly off one of the symmetry axes, so we can have them a little bit away from the exactly 180 degree. So we call them 180 plus minus 5 degree domains. So they can be slightly tilted with a small angle with each other, which is phi. Phi is usually a very small angle. Okay, so from that, we are using this method to identify two types of domains. We just analyzed the response of this 180 plus minus 5 domains. How about the response from a classical ferroelastic domains? So we basically performed a very similar method on another high-resolution Bragg reflection, which has two components. So we move on to the 111 peak. In this case, it's two peaks. So we call them, we can't really call them two peaks because they are a group of peaks. So we call them group 1 and group 2. So here are the YZ slice of group 1 and group 2. We selected 5 boxes in group 1 and 3 boxes in group 2. Basically, they show very similar behavior as the previous peak that I discussed. For example, the overall X-scan showing very nicely group 1 and group 2 response like a classical Bragg reflection, 1D reflection. And this is an example of this group 2 in box 1. And still, we can see first of all, a very different response from the overall response. And also, they show a shift of the center of mass of intensities from plus field to the minus field. So we can perform the same pipeline analysis, mapping the d-spacing shift from the very small box to the very big box and plot them as that. The only difference is now we have 2 groups. So each of these calculations, this d-spacing change, they only represent the information of one peak. So we can't say it's extrinsic. It's more or less intrinsic. For example, like here, with the smallest box size, they are purely intrinsic. And when we move on to here, it is a sum up of several 180 plus minus 5 domains, and we call them cumulative intrinsic because it's obviously different from the classical extrinsic. to calculate the extrinsic response, we did this very simple estimation that if we apply a different field, we have average position of x, which is d-spacing. By changing the field, the delta x can be written like that. And based on the fact that we do observe an intensity exchange between two peaks, and we find out that the only reason to make the intensity change in each of them is only intensity exchange. So delta I1 is basically the same as delta I2 with a different sign. So by rewritten this equation, we can separate the contribution of delta x into two parts. The first part only involves a change of intensity, and it's related to the position of these two peaks, but it doesn't involve any change of the x. And the second part, it doesn't involve the change of the intensity, but only involve the change of the d-spacing. So this part is more or less related to the intrinsic effect. And by this is a reflection of intensity exchange, so it is related to the pure extrinsic effect. So we've got all these values, and we can calculate them, the final effect. So this red dot is basically an average of the intrinsic effect from group 1 and group 2. And this blue cross is the calculation of the extrinsic effect according to the first part of the equation. So from this crystal, we can estimate about 80% of the electromechanical contribution is from the extrinsic effect. But here I'm trying to demonstrate this method because when we change a crystal or when we change the electric field, basically, this absolute value must be different. But anyway, I hope I'm demonstrating that by taking a single high-resolution multi-domain single crystal diffraction experiment, we can get information about the electromechanical response at different length scale at the same time. So we can get the information about polarization rotation from something like that, and by selecting the very small boxes. And also, we can get information about 180 plus minus 5 domains by analyzing different small boxes within one reflection group with similar d-spacing. And finally, we can calculate the overall response from classical ferroelastic domains. And by having that, hopefully, in the future, we can separate these responses with different materials, and by that, we can find a way to further improve the piezoelectric response of different materials. So that's all. Thank you.
Okay, so questions.
Thank you. So have you tried to evaluate the Wang scattering, the diffuse scattering around, which would give you the characteristic grain size?
In our following experiment, we did that. But for this experiment, it's actually to collect the data with high resolution reflection and to collect data with diffuse scattering intensity are a little bit different. So we can collect diffuse scattering intensity that we did in a following experiment. But this one, we only collected the main Bragg reflection. Yes? Sorry, unfortunately, I don't remember the exact value. Maybe we can discuss later. Thank you.
Just a quick question. I probably missed it earlier, but what's the size of the instrumental resolution on one of these pictures, like compared to your small box size?
What do you mean by instrumental resolution?
So if I just had a boring single domain and I saw this blob, how much bigger is this blob compared to the intrinsic resolution of the instrument?
Well, when we talk about the detector resolution, okay, if we want to compare with one of these maps, it's I think a pixel should be about 1/100 of one of these reflections, as far as I remember. Is that your question? So we
not exactly, but maybe we can talk after. Thank you.
Oh, okay. So.
Nice talk. Do you have a feeling how big is phi?
How big is phi? We have an estimation from the different position of the from that, I think. So they are at slightly different d-spacing, so the phi must be small. But yes, it's a good idea. We should calculate it, really. According to this, it's actually very small.
Okay, so let's thank the speaker again.